Hey guys, welcome to our notes for Chapter 8, Section 3. Today we are going to talk about triangle similarity by side, 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 and side, angle, side. So today our learning targets are to learn two new similarity theorems, or two ways to prove two triangles are similar. That's the side, side, side. So all three corresponding sides are proportional, and then our two triangles will be similar. Or side angle side, where we have two pairs of corresponding sides that are proportional and their included angles are congruent. All right, we want to try to use similar triangles to prove things about slopes of parallel and or perpendicular lines. Let's take a look at our first theorem. Here, side, side, side similarity theorem says if corresponding side lengths of two triangles are proportional, then the triangles are similar. So over here on the right hand side, we've got two triangles, ABC and RST, and we say that if AB and RS are in a proportion, and that proportion is equal to, or I should say a ratio, and that ratio is equal to BC over ST, and that ratio is equal to CA over RT, then we say that these two triangles are going to be similar to each other. All three corresponding sides are proportional. All right, our next theorem then is the side angle side. Very similar, however, now we have an included angle between the two sides that are proportional. So this theorem says if an angle of one triangle is congruent to an angle of a second triangle and the lengths of the sides, including these angles, are proportional, then the triangles are similar. So if we take a look at the example that we've been provided, we've got angle X is going to be congruent to angle M, and then we also know that ZX and PM are in a ratio that is proportional to or equal to XY over MN. So here we have this case of a side angle side similarity. Okay, so these two triangles will be proportional and therefore they will be similar triangles. All right, let's get into some examples of what we are learning about in this section. Example 1 asks us to determine if the triangles are similar or not. If so, explain and write a similarity statement. So the two triangles that we want to prove are similar are this yellow highlighted one, so this top yellow one, and then the larger blue outlined triangle. So we're going to take and see that they both have this triangle, or sorry, this angle x, right? WXY triangle contains the angle x, and so does VXZ. So we have one included angle that is congruent, right? Angle x is congruent to angle x by that reflexive property. Next thing, we want to check and see if our sides are proportional. So we have this side here of the smaller triangle XW, and that's equal to 15. We're going to put that over the larger triangle side, which is 15 plus 20, or 35, and that's represented by the side XV. All right, so first ratio here we said was 15 over 35, and we're going to test and see if that is equal to, here's 27, or XY, over the larger one, which is X to Z. All right, so that's the side lengths of 27 over 27 plus 36 is 63. Okay, so we want to determine if 15 over 35 is proportional to 27 over 63. If this is a true proportion, then we can say that these triangles are similar by side angle side similarity theorem. So let's reduce these and see if they both reduce to be the same thing. I know that 5 goes into 15 3 times, 5 goes into 35 7 times. So that's going to reduce to 3/7. Likewise, I know that 9 goes into 27 3 times, and 9 goes into 63 7 times. So yes, these both reduce down to the same ratio, 3/7. So we're going to say triangles are similar by side angle side similarity theorem. Okay, and we're going to write the triangle similarity statement here. So we got triangle WXY is similar to triangle VXZ. Okay, if at any point you're a little bit confused or we're going too fast, just pause the video, rewind the video, and rewatch an example. Let's move on to example 2. We have triangle ABC. It has side lengths 42, 21, and 35. The shortest side of a triangle that's similar to triangle ABC is 9 units long. Find the other lengths of the triangle. Okay, so in other words, we have triangle ABC, and it's similar to another triangle. We'll just call it DEF, even though we're not given the letters. We know the side lengths of ABC are 42, 21, and 35. Well, we're told that the shortest side of the other triangle that's similar to it is 9. So we know that we need to match that up with the shortest side of ABC, which is 21. So if these two triangles are similar, then these three ratios will be all equal to each other. So we can find the lengths of the other two sides by just taking two of these ratios, setting them equal to each other, and solving for x. Okay, well, I know going from 21 to 42, I'm going to double 21 to get to 42. So if I double 9, x should be 18. So that looks like that's the largest side of my other triangle. Now I'm going to isolate my other two, my other two ratios, and I'm going to solve this side for y. So I'm going to do the cross multiplication on this one. That's 21y equals 9 times 35. So that's 270. I'm going to quick do this in my head. 270 plus 45. So that's, what is that, 315. All right. So we're going to take 21 into 315, and that's going to give us our value for y, which will be our other side here. And I don't have my calculator here, so I'm going to let you guys punch that into your calculator, and you come up with the length of side y. And that's going to be the other two lengths of the sides of the triangle, I should say. It's going to be the other two sides of the triangle that we don't know. All right, moving on, example 3. We want to find the values of x, y, and z that make triangle DEF similar to triangle HGF. So if I take a look here at my triangles, DEF is this top left-hand corner here, and I see that this angle and its other angle across from it are vertical angles, so it's going to share that angle here. And if these triangles are going to be similar to each other, then I could say by side, angle, side, that these triangles will be similar. All right, so that means this side DF must be proportional to this side here FH. And it also means that side FG must be proportional to side EF. And finally, we know that side GH has to be proportional to side DE. Well, before I find x, y, or z here, it looks like I'm also told that this angle measure is 2 times x minus 4. Well, this angle G has to correspond to my angle E, and corresponding angles in similar triangles are congruent. So I can find my value here for x by dividing my 2 over x minus 4 now is equal to 8. Add my 4, x is 12. All right, once I know the value of x, I can substitute that value in here for my expression for EF, 12 minus 5. So I know EF here must be 7. So it looks like if EF corresponds to FG and EF is 7, FG is 14, it looks like my small triangle DEF must be half the size of my larger triangle FGH, because they're in this proportion of 7 over 14, which reduces to 1/2. Okay, that means here that 3y and 24 are in that proportion. This 24 is 1/2 of whatever 3y is. So 3y must be equal to twice 24, which is 48. If I divide off that 3, y now is equal to 16. Okay, and then finally, we're going to set 6z plus 8 has to be equal to twice the size of 25. So in other words, twice 25, is going to give me 50. So 6z plus 8 must be equal to 50. All right, you're going to solve for z there by subtracting your 8 over and dividing by 6. You should get a z value of 7. Okay, so just using similar triangles and the idea of proportionality here to find those missing angle measures. For our final problem of the day, we've got a proof. We are told that line L and N are parallel to each other, and they are non-vertical. And we want to prove that the slope of line L is equal to the slope of line N. All right, well, remember that slope is your rise over your run. All right, it's just a ratio. So if I can show that the ratio of the rise over the run of line L is equal to the rise over the run of line N, then I will show that these two slopes are equal. Now, rise and run are just parts of our triangles here. Okay, our rise is this BC, our run is AC. Okay, in one triangle. And then the other triangle, our rise is EF, and our run is DF. So use this idea that you're going to show these ratios are equal to each other because you have similar triangles. Those ratios will be proportional. All right, so that's what I want you to do. Give it a shot. We can check this in class tomorrow, but show that these two triangles are similar to each other, and therefore their corresponding sides are proportional.